Hi, my name is Nimrod Crawford, and today we'll be discussing the use of alcohol-based fuels in off-highway high-performance applications. So first off, we're going to look at the requirements of an off-highway performance fuel. We're going to look at alcohol and how it fits into these requirements, and we're going to look at optimizing for alcohol-based fuels. So these are important aspects to consider when choosing a high-performance fuel. First, we have octane, which is the ability of the fuel to resist detonation and or maintain stable combustion after the spark plug fires. We have burn speed. This is the speed in which the flame propagates across the combustion chamber, which influences things like timing. Energy value, which is the amount of energy that is released when the fuel is combusted, and the cooling effect. This is linked to the latent heat of vaporization value and has to do with how much energy that the fuel absorbs from its surroundings as it vaporizes in the intake and combustion chamber. So what is alcohol? Ethanol and methanol are both renewable fuels that can be produced from plant matter such as corn and wood. Both are also biodegradable. Ethanol is currently already used in 98% of pump gas sold in the United States as an octane booster and an oxygenate. Types of alcohol fuel include ethanol, methanol, butanol, MTB, DME, and TBA, but for this presentation, we will mainly focus on ethanol and methanol. Environmental benefits. Ethanol is water-soluble and is safer for groundwater than petroleum pollution. Ethanol and methanol can be produced from renewable biomass feedstocks that include wood, waste crops, and potentially other forms of biological organisms such as algae in the coming future. Ethanol, when produced, is an energy net positive, meaning that it takes less energy to produce a gallon of ethanol than the gallon contains in heating energy. So here we're going to take a look at how ethanol and methanol both compare to 100% gasoline. So here we have three fuels from VP Racing Fuels. They include VP 110, which is a leaded racing gas, which is 100% gasoline. We have VP E98, which is 98% ethanol. And we have the VP M1, which is 100% methanol. So if we take a look at the AKI values, which would be the values that would be on a U.S. pump handle, we have the VP 110, which has an AKI of 109.5. The E98 has an AKI of 111.5, and the VP M1 has an AKI of 111. The energy content of the three fuels are as follows. The VP 110 has 116,000 BTUs per gallon. The VP E98 has 76,330 BTUs per gallon. And the VP M1 has a energy content of 57,250 BTUs per gallon. The latent heat values are as follows: 155 BTUs per pound, 396 BTUs per pound for the ethanol, and 503 BTUs per pound for the methanol. Burn speed are as follows: 0.4 for the 100% gasoline, that's meters per second, 0.6 meters per second for the 98% ethanol, and 0.62 meters per second for the 100% methanol. So as you can see, the two alcohol fuels are superior in every category except energy per gallon, but there's a little bit more to that as far as burning these fuels in an internal combustion engine. And I will show you on the next slide how you will see an increase in performance with the alcohol-based fuels, even though they don't have the energy content of the gasoline-based fuel. So here we look at how the air-fuel ratios factor in during the combustion to determine the overall available thermal energy. So in order to do that, we have our BTUs per gallon, but we also need our pounds per gallon of each fuel. So if we look over at the chart on the upper right-hand side, we will see we have our stoichiometric ratios. So what the stoichiometric ratio is basically a mass to mass ratio. So if we have 14.7 in terms of the gasoline pounds of air, we can combust 1 pound of gasoline. When we look at ethanol, the value drops. This is due to the fact that ethanol is an oxygenated fuel and carries some of its own oxygen to support combustion. Therefore, it doesn't need as much outside oxygen. So we can combust you can combust 1 pound of ethanol with only 9 pounds of air. And if we move down to methanol, it continues to lower. So we can combust 1 pound of methanol, with only 6.47 pounds of air. So if we look at our equation in the middle of the slide, we can begin to see how the numbers will all work out in order to be able to achieve more energy availability. So if we take a given air mass of 7.65 pounds, and we take that and divide it by the stoichiometric ratio, we will see that that will give us an available fuel mass to combust. We will then take that fuel mass, times it by the BTU value over the pounds per gallon. This will give us our available thermal energy. So as you can see with this equation, the lower the stoichiometric ratio, the more fuel mass that you can combust, and thus the more BTUs that you will have available in order to produce power within the engine. This causes our heating values to flip, or our thermal energy availability to flip. So now gasoline has the lowest at 9,574. Ethanol will have the middle at 9,830, and then methanol becomes the highest energy availability with that given air mass at 10,288 BTUs available. So, how to optimize an engine to take advantage of this. So as you can see, the main thing that's going to be needed is more fuel is going to be needed to be delivered to the engine. So how to calculate the needed amount of fuel, we have this equation here. This will help in sizing components such as injectors, fuel pumps, and fuel lines. So in order to complete this equation, you will need a few variables. This includes the volume of the engine, the volumetric efficiency of the engine, the pressure in the intake manifold. This can be atmospheric, above atmospheric, or lower than atmospheric if it's a restricted application, or force inducted. And you're also going to need the RPM at which the max horsepower is reached, the desired air-fuel ratio, and the inlet air temperature. Now, with the desired air-fuel ratio, when tuning for performance, stoichiometric is not always desired. At maximum horsepower, the air-fuel ratio will be more towards what's known as the RBT value, or rich best torque. This is because during the intake stroke, a finite amount of oxygen is induced into the cylinder, And since combustion is not perfect, oftentimes more fuel is injected in order to ensure that all the oxygen within the cylinder is converted into energy. So for our example, we're going to use a GM LS7 engine. It has a displacement of 7 liters. It has a volumetric efficiency of 95%, just roughly estimating. KPA of 101.325, which is atmospheric pressure, since this is a naturally aspirated engine. It's going to have peak horsepower at 6,300 RPM, and we're going to keep our inlet air temperature stable at 293 Kelvin, which is approximately 20 centigrade, or I believe roughly 60 degrees Fahrenheit. So for the gasoline, we'll have an RBT value of 12.6 to 1. With the ethanol, our RBT value will be roughly 6.43 to 1. And with the methanol, our RBT value will be roughly 4.8 to 1. So as you can see, our fuel requirements with the gasoline is 1,150 liters per hour using our formula on the previous slide, 2,253 liters per hour for the ethanol, and 3,018 liters per hour for the methanol. So as you can see, the fuel requirements almost double from going from gasoline to ethanol and almost triple in going from gasoline to methanol. So as you can see, some substantial upgrades could be necessary to be able to take part in the benefits that alcohol fuel can give an engine, in order to ensure that you don't exceed 80% duty cycle with your various components, such as the fuel injectors or your fuel pump. So just to recap, alcohol-based fuels more than have the capability to replace leaded gas and are better for the environment. Due to the increased fuel flow, fuel system upgrades are necessary to ensure optimal performance, as we saw in the previous slide. And power increases can be seen in the neighborhood of 3 to 7% just in changing fuel, with more available through its other properties, including its high latent heat value and faster burn speed, which can influence things like timing and intake air temperature, which can influence things like the density of the air charge, which all play a role in how much power an engine will produce. Thank you for listening.